There she goes.
Sure is big.
I hope it floats.
It's a little late to worry about that now.
Look, it's floating!
5 me!
One concept that is very crucial to understanding the behavior of fluids is buoyancy. Buoyancy can be defined as an upward force exerted by a fluid that opposes the weight of an immersed object. One explanation for buoyancy is provided by Archimedes' principle. Archimedes' principle states that when an object is immersed in fluid, it is buoyed up by a force equal to the weight of the fluid that it displaces. Buoyant force on an object in a fluid is given by F equals rho times G times V, where rho is the density of the liquid or fluid in which the object is, G is the coefficient of gravity, and V is the volume of the object in the fluid. Buoyancy is very interesting to think about because not only is buoyant force reliant upon the amount of volume displaced by the object, it's also dependent upon the weight of the fluid itself. Let's pretend for a moment that this crudely drawn shape is really a cruise liner at sea. Now, this cruise liner will sink if the weight of the water displaced by this section does not exceed the total weight of the entire cruise liner. One important thing to note when dealing with boats is the change in density of water. For example, if you have a boat that's loaded down out at sea and you're in salt water and you start to move towards the river, your boat will actually start to sink more because fresh water is less dense than salt water. So the water that your boat is displacing will weigh less than it did when you were out at sea, causing the boat to sink. Let's say we wanted to figure out whether this 1 kilogram block would float or sink. We'd have to go back to the equation buoyant force is equal to rho times the coefficient of gravity times the volume of the object. So we've already stated that the mass of this block is equal to about 1 kilogram. Let's also assume that it's a square block with sides equal to about 0.5 meters. The next step after we have the measurements is to cube the sides to find the volume of the box. And when we do that, we get the volume comes out to be about 0.125 meters cubed. The next components necessary to figure out the force are rho and gravity. The generally accepted value of rho for fresh water is about 1,000 kilograms per meters cubed. This means that for every cubic meter of water, there will be 1,000 kilograms of mass. The generally accepted value for gravity is 9.8 meters per second squared, and that is the average value for gravity on Earth. Assuming that this block is on Earth, this gravity value is correct. The product of all of these is a 1,225 Newton buoyant force. However, our mass of our block is in kilograms, but that is an easy fix because all we need to do to find the weight is multiply the mass by the coefficient of gravity, which is 9.8, so that gives us 9.8 newtons. This whole problem has been done assuming that the entire block is submerged. However, with this large of a buoyant force, it will continue to push up until the buoyant force acting upon this block by the submerged volume is equal to the mass of the block. When considering the interaction between the object submerged in the fluid and the buoyant force on the object, just remember that there are really only 3 possibilities. If the weight of the object is greater than the buoyant force, the object will sink. If the weight is exactly equal to the buoyant force, the object will be suspended in the fluid. And if the weight is less than that of the buoyant force, the object will rise in the fluid. The next time you watch a balloon float away, or you watch a ship sail down a river, just remember that you're watching buoyancy at work.